Okay, we will begin our next chapter, chapter 6. And in this particular video, we will be covering two sections because they are very much related to one another. So instead of making two separate videos for each of the sections, I'm going to just make one video for sections 6.1 and 6.2 because they all deal with, both of those sections deal with what we call the laws of exponents. And there are 7 different laws that you will need to know. And each law by itself is not particularly difficult. It's the complexity of the problem that incorporate multiple laws within one problem. That's what sometimes makes it a little bit more difficult, because it's a matter of remembering which laws you need to apply, because there are 7 different laws. You don't have to apply them in any particular order. You usually try to follow, once again, the order of operations even when working with these laws of exponents. So, like I said, there are 7 different laws. I'm going to break them down one at a time and show you an example, and build upon them, all right? So, our very first law of exponents deals with if we have a to the m being multiplied with a to the n power. And this is in fact equal to the base a to the m plus n power. Now basically, in words, when multiplying the same bases, as we see that we are doing here, base a, when we are multiplying the same bases, basically you are going to keep the base and add the exponents. That's what we're looking to do here. Okay, so whenever you are multiplying the same bases, you don't do anything with that base. You keep the base and you add the exponents. For example, let's say we have x to the third being multiplied with x to the fifth. Here's a case where we would apply and use this first law of exponents, because we have the same base x and they are being multiplied, in which case we're going to keep that base x and we have to add the exponents, and 3 plus 5 of course gives us now an exponent of 8, and that would be your simplified expression. Let's say, for example, we had a negative 4x to the fifth being multiplied with maybe a 3x to the sixth power. And we want to simplify this. Well, we would want to multiply the negative 4 with the positive 3. And that, of course, would give us a negative 12. But now we want to use that law of exponents because we are multiplying the x's together. That's the same base. We're going to keep the base and we will have to add the exponents. So 5 plus 6 would give us a total of the exponent of 11. And that would be your simplified expression. Let's just do one more. Let's say we had x to the fourth y being multiplied with, let's say, x to the sixth y to the third. Now once again, we want to multiply the same bases. So I have an x here being multiplied with an x here. And so we're going to keep that base x, and we have to add those powers. And 4 plus 6 more would give us x to the 10th. And then we have a y here, and we have a y here that are also being multiplied. And so once again, we would have to keep that base y, and we have to add the powers. Now be careful here. It's obvious in the second y that it has an exponent of 3. But remember, if you see just a variable y, or any variable for that matter, there is an understood exponent of 1. And so y to the first times y to the third would give us y. We have to add those powers. y to the 4th power. Okay? So if you have multiple variables, you only combine those variables that are the same. Notice, don't combine the x with the y here. We're not going to add the 10 and the 14 because they are not the same base. Okay? And that is our first law of exponents. The second law tells us that if we have a to the m raised to the power of n, that is going to equal that base a to the m times n power. And basically what this is saying, when a power is raised to another power, you want to multiply the powers. So you don't do anything with the variable or the base in this particular case. All right, so when you have a power raised to another power, which is the case here, the power of m is raised to a second power of n, you have to multiply those powers. And let's just look at some examples where we would use the second law. For example, if we have x to the 5th squared, well, here is a case, as we can see from our law, that we have a power of 5 being raised to the power of 2. Power to a power, we have to multiply those powers, in which case we would have x to the 10th. And that would be your simplified expression. Let's just do another one. Let's say we had x to the 3rd to the 4th being multiplied with x to the 5th to the, let's say, 7th power. And we want to simplify this. Well, the first thing that we would have to do is actually we would use the second law of exponents, because we have a power raised to another power, and we have the power of 5 raised to another power of 7. In which case now we would have x, 3 times 4 would be 12, times, if we have x to the 5th to the 7th power, that would give us x to the 35th power. But we can't stop there, okay? That's not considered simplified, because now we have the two variables, the same base x, that's being multiplied. So according to our first law now, we would want to add these exponents, in which case now we would have just a singular x, and if we take 12 and add the 35, that would give us x to the 47th power. That would be your simplified expression for that particular problem, okay? So you're always looking to simplify as much as possible, all right? So we did the second law first, and then we had to use the first law of exponents to finish off the problem. So that takes care of the second law. Our third law tells us if we have a times b, two different bases, to the power of m, that is going to equal a to the m times b to the m power. Because what this law is telling us is that you can distribute a power over multiplication, which is what's taking place here. We have the two bases, a and b, that are being multiplied, okay? And then they are being raised to a power. So we can distribute that power of m over the multiplication of those two bases, a and b. For example, if we had 4x to the 3rd power, well, what we can do is we can use the third law of exponents, in that I would take the 4 and raise it to the 3rd power, and then I would have to take the x and raise it to the 3rd power. Well, 4 to the 3rd power, be careful here. Common mistake, 4 to the third, sometimes people think the answer is 12. But that would mean 4 times 3, and that's not what that is. 4 to the third power means 4 times 4 times 4, which of course is 64. And then of course we have x to the third power, and that's as far as you can go with that simplified expression. We were able to distribute the exponent of 3 on both the 4 and the x because they are being multiplied together. Let's try another example. Let's say we had x to the fourth, y to the third squared being multiplied with x, y to the fifth cubed. We want to simplify this as much as possible. Well, I'm going to follow pretty much the order of operations. I look inside my first parenthesis, and there's nothing that can be done. I look inside my second parenthesis, and there's nothing that can be done. Next, after parentheses, comes, of course, the exponents. Well, I have this exponent of 2, and I have this exponent of 3. And according to the third law of exponents, I can distribute those exponents over the multiplication inside these parentheses. So what's going to happen is that you're going to have x to the fourth squared, y to the third squared, because I can distribute the power of 2 on these two things being multiplied. Then I have to do the same thing here. That would give us x cubed, and of course y to the fifth cubed. And that could all be done once again because of our third law of exponents. But now the second law tells us that when we have a power to a power, we want to multiply those powers. And so x to the fourth squared would become x to the eighth. Y to the third squared, power to a power, when we multiply, we would get y to the sixth. This, of course, means x to the first to the third, and that was how we would get x cubed. And then finally, y to the fifth to the third would give us y to the 15th power. In all four cases where we had a power to a power, we had to multiply those powers. That was because of the second law. But we're still not done, because now we can actually use the first law of exponents. Because I have an x here and an x here, they are being multiplied. So according to that first law, we're going to keep that base, and we would have to add the powers, giving me x to the 11th power. Same thing with the y. They too are both being multiplied together, so we're going to keep that base y, and once again we would have to add the exponents. So 6 plus 15 would give us 21. And that would be your simplified expression. This was the original, and what we have here is your simplified version. We're trying to eliminate any and all operations, and we did. We eliminated a lot of the multiplication, as well as we eliminated the exponents that were taking place. Okay? You're looking to get it down in terms of one variable of each. Okay? X to 1 power and y to 1 power. And that is because of the third law of exponents. A fourth law. Remember, I said that there are 7 in total. The fourth law is just the opposite of actually the first law. Because if I have a to the m being now divided by a to the n power, that is going to give us a to the m minus n power. Basically what this is saying, when you divide, as we are doing here, the same base, once again what we want to do is keep the base, except now what we have to do is subtract the exponents. You may recall from the first law that when we were multiplying the bases, you added the exponents. Here now that when you divide the same base, you're going to still keep that base and you're going to subtract the exponents. Now, when we are doing this one, a few things to keep in mind. First thing we need to determine is where the base A is going to go, okay? So you are going to, first of all, put the base where the larger power was. So if your larger power is in the numerator, A is going to stay in the numerator. If the larger power is in the denominator, the base A will stay in the denominator. And then what you always want to do is you always want to take the larger power and then you want to subtract the smaller power. You always want to do that, okay? Let's take a look at an example or two. For example, if I had x to the 8th divided by x to the 5th. Here we're going to need to use the fourth law of exponents. Because I am dividing the same base, I have to subtract my powers. But first I want to determine where the x is going to go. So I look at my exponents, and I'm going to put x wherever the larger power is. And since 8 is the larger power, x is going to remain on top. And now I have to subtract the exponents. And you always take the larger and subtract the smaller. 8 minus 5 would give me a simplified expression of x cubed. Okay? And that would be your answer. Be careful. Okay, for example, let's say we had the following. X to the 6th over x to the 10th. Now, once again, we want to simplify this using that same fourth law of exponents. Well, first of all, I need to determine where the x variable is going to go. And I had said to always put the variable, that base, where the larger power was. And since the larger power is 10, x needs to remain in the denominator. And now I'm going to subtract. I always take the larger power, 10, and I'm going to subtract the smaller power, 6. So 10 minus 6 gives me an exponent of 4. But be careful. Right now there's nothing on top, okay? The numerator, the top part of the fraction, always needs to be represented by something. And in this particular case, we would have to put the number 1. So the correct simplified expression would be 1 over x to the 4th. If the variable stays in the numerator, you don't need anything in the denominator, okay? You could write x to the 3rd, and if you wanted to, you could put a 1 on the bottom, all right? X to the 3rd over 1 is the same thing as x to the 3rd, okay? But it's optional, and that's why I wrote it in a slightly different color, okay? But if you have the denominator, okay, is where the variable is located, as in the second example, the 1 that's in the numerator must be there. A 1 in a denominator is optional. Okay, you don't have to put the 1 there, all right? Let's try another one. Let's say we had x to the 5th, y to the 10th, over, let's say we have x to the 3rd, y to the 14th. And we want to simplify this. Well, let's take a look at my variables. I'm going to simplify those bases that are the same. So I usually work with them alphabetically, so let's start with the variable x. We need to determine where x is going to go. Since the exponent 5 is larger than 3, x will remain up top. And when we subtract now 5 minus 3, we get x squared in the numerator. Next, let's do the variable y. Okay, let's first of all determine where y is going to go. Since the exponent of 14 is larger than the 10, y will stay in the denominator. And now we have to simplify by subtracting the powers. 14 take away 10, of course, would be 4. And that would be your simplified expression. We got it down to a single x and a single y. Okay, we don't have multiple x's or multiple y's within the same problem. Okay? Let's try another. Let's say we had 24 x to the 8th, y to the 10th. I'll throw in another variable, z, let's say to the 3rd, over. Let's say we had 16 x to the 10th, y to the 5th, z. And we want to simplify this. Okay? Why don't you try this one on your own? Pause the video at this point, try to work through the problem, and then when you're done, turn the video back on, and let's see how you made out. Well, I'm going to start by simplifying my fraction. Okay? I have the fraction of the numerical fraction 24/16. Okay? Well, 24/16, that is a fraction that can be simplified because both 24 and 16 are divisible by 8. 24 is divisible by 8 3 times, and 16 is divisible by 8 twice. So 24/16 is the same thing as 3/2. Next, let's do the variables. Once again, I like to do them alphabetically. So I start with x, and x is going to remain in the denominator because the larger power is 10. And then when we subtract, 10 take away 8 leaves us with an exponent of 2. Next, we have to take a look at the variable y. Where is y going to go? Well, 10 is the larger power, so y stays up top. And now when we subtract, 10 minus 5, we get 5. Finally, now let's do z. Once again, let's first of all determine where z is going to go. Since the exponent 3 is larger than the exponent of 1, we will keep z in the numerator. And when we subtract now, 3 take away 1, we get z squared. And that would be your simplified expression. Okay? That's what the laws of exponents allow us to do. Simplify these expressions. A fifth law. The fifth law is actually similar to the third law. The fifth law tells us that if we have a over b to the power of m, this is going to, in fact, be equal to a to the m over b to the m. Because much like the third law, you can distribute, once again, a power over division. If you can distribute a power over multiplication, you can also distribute a power over division. So let's just do an example or two. If we had, let's say, x over 5 to the third power. Now what we want to be able to do is to distribute the exponent of 3 over this division. So we would have x to the third over 5 to the third. Well, we can't do anything with the x to the third. However, 5 to the third power, 5 times 5 times 5, 125. That would be your simplified expression. If we had, say x squared y to the 4th over x to the 8th y. Let's say that whole quantity now is going to be raised to the 4th power. Now, there's a couple of ways you can handle this problem. What I suggest doing is working inside the parentheses first, okay? Because that's pretty much following the order of operations. And if you can do anything inside a parenthesis, it probably might be to your advantage to work with inside the parentheses first. And according to actually the 4th law, I could simplify my x's and my y's because they are being divided. Let's determine where x is going to go. Well, x has to stay in the denominator because 8 is the larger power. 8 minus 2 would give us an exponent of 6. So I have x to the 6th in the bottom. Now let's take a look at the y's. First of all, let's determine where y is going to go. I have a y that's going to remain on the top, and we have to subtract the powers. 4 take away 1, of course, would be 3. And then that still needs to be raised to the 4th power. And that's where, once again, the 5th law of exponents comes into play, because I can distribute the outer exponent of 4 on these two bases. So that would give me y to the 3rd to the 4th, and in the denominator we would have x to the 6th to the 4th. Well, now what's actually being demonstrated as I go through these step by step is the 2nd law, because I have a power to a power. And when we have a power to a power, the 2nd law tells us we have to multiply the powers. And that's why we would get y to the 12th over. And in the denominator, I also have a power to a power. So according to the 2nd law, we'd have to multiply. And that would give us x to the 24th power. That would be your simplified expression. Okay? So work, I would suggest, inside the parentheses first. Simplify what you can inside the parentheses before working external with the exponent. Okay? That's your 5th law. The 6th law is probably the easiest of all the laws, but sometimes people get confused by it. If I have a base A and I raise it to the 0 power, it will always equal a number. And that particular number happens to be the number 1. Okay? Anything at all to the 0 power is the number 1. That is your simplified expression. So if I have the number 5 to the 0 power, that's 1. If I have the variable x to the 0 power, that's 1. If I have, let's say, 45 x to the 10th, y to the 72nd, over 81 x to the 3rd, y to the 56th, and that whole thing is raised to the 0 power, don't drive yourself crazy, okay? The fact that what's inside the parenthesis is raised to the 0 power, the whole thing is nothing more than the number 1, okay? So anything raised to the 0 power equals 1, okay? Whether it be a simple number, a simple variable, or this complicated algebraic expression. By raising it to the 0 power, it's nothing more than the number 1. Now, the 7th law, our last law for this particular lesson, okay, is actually a two-parter, okay? If you were to look back at all the problems that we did, you'll notice one thing is true about the exponents. And you'll notice that all of the exponents that we were working with were positive numbers, okay? Even in this most recent crazy example, we had an x to the 10th, y to the 72nd, x to the 3rd, y to the 56th. Those are all positive exponents, okay? The initial problems were all positive exponents, as well as your final answer had all positive exponents in the end. Now, the seventh law, the last law of exponents that we're dealing with, addresses what happens should we encounter exponents that are negative numbers. Never have your final answer with negative powers, negative exponents. So we need a way to get rid of negative exponents should we encounter them, okay? So our seventh law, like I said, is a two-parter. Part one tells us that if we have a to the negative m, that is going to equal 1 over a to the positive m. Of course, the opposite is also true. That if I have 1 over a to the negative m, that will equal a to the positive m. And let's just see what took place here. Basically, what I did was I changed the location of the base. Initially, a was here in the numerator, okay? And since that a was being raised to a negative power, I needed to get rid of that negative power. So what did I do? I took the base a, its location, and I dropped it into the denominator of a fraction. And when we do that, that changes the exponent from negative to positive. The same is true should you have a base a with a negative exponent in the denominator. We need to eliminate that negative exponent. And the way that we could do that once again is to change the location, the position of the base. Once again, now base a moved out of the denominator into the numerator, and that changed your exponent from negative to positive. Okay? All right, so let's take a look at some examples involving this seventh law. If I had x to the negative fifth, that would equal 1 over x to the fifth. If I had, let's say, 3 over x to the negative sixth, that is going to equal 3x to the sixth. Notice, once again, I changed the location of the variable. X went into the denominator, and it changed the exponent from negative to positive. Let's take a look here. I had to get rid of this x to the negative sixth power. I didn't do anything with the 3. All I did was move the x from the denominator up to the numerator, and that also changed the exponent from negative to positive. What if we had x to the negative eighth over y to the negative third? Well, now I have to eliminate both negative exponents, okay? So if I need to eliminate both of these negative exponents, I have to change both bases, in which case now I would have y to the third on top and x to the eighth on the bottom, okay? Never, ever leave your answer with negative exponents. The final answer should always have positive exponents, as we've been seeing. Let's try a few others. Let's say we had x to the eighth, y to the negative third, z to the negative fourth, over, let's say we had x to the negative third, y to the negative fifth, z squared. Okay. We want to simplify this. We want to simplify it as much as possible, as well as have your final answer with only positive exponents. Now, what I'm going to recommend doing here is first and foremost, eliminate any exponent that's negative. Only the negative exponents are we going to affect right now. Anything that has a positive exponent, we're going to leave alone. So that means x to the eighth, I'm going to leave that alone. I'm not going to touch that right now because it already has a positive exponent. This x has a negative exponent, so what I'm going to have to do, according to the seventh law, is change the location. So that means x to the third is going to go on top. Now let's do the variable y. Okay, I like to work with my variables alphabetically. So both of these y's have negative exponents, so I'm going to have to change both of them. So that means y to the negative third that was on the top goes into the bottom, y to the third. Y to the negative fifth, that's in the bottom, I have to move that up to the top. Next, let's go with z, okay? Z to the negative fourth, that's on the top, so I got to get rid of that. That would give me z to the fourth in the bottom. And then z squared, since that's already positive, let's leave it as such, z squared. And now, let's see what else we could do to further simplify this, because I see multiple x's, y's, and z's, and we can only have one of each. So the x's are being multiplied, okay? So that goes back to the very first law of exponents. So I'm going to keep the base, and I'm going to add those powers, in which case 8 and 3 gives us an x to the 11th power. Next, let's go with the variable y. Okay, we have a y in the top being divided by the y in the bottom, and that, of course, takes us to the fourth law of exponents, which means we have to subtract them. But where's the y going to go? Remember, we place the y where the larger power is. And since 5 is larger, y is going to stay up top. And when we subtract 5 minus 3, we get 2. Lastly, we have to do the z's. They're being multiplied. So that takes us back to the very first law, which means we have to add those powers, giving us z. And when we add them, we get z to the 6th. And that would be your simplified expression. Okay? You'll notice all of the final exponents are positive. Okay? So that's what we need. You need to have one of each type of variable, okay? And you need to have all positive exponents. Let's just try a few others. Let's say we had maybe x to the negative third, y to the negative fifth, z to the negative sixth, over x to the negative eighth, y to the negative second, z to the negative 10th, and that's all going to be raised, let's say, to the third power. Once again, what I would recommend doing, okay, since I know I can't have negative exponents in the beginning, I want to get rid of all the negative exponents that we were initially had here. So since they all have negative exponents, I'm going to change the location of all of them, which means x to the negative third goes in the bottom. X to the negative eighth must go up top. Y to the negative fifth goes to the bottom. Y to the negative second, that's got to go up. Z to the negative sixth, bring that down. Z to the negative 10th, I'm going to move that up. I got rid of all my negative exponents, okay? Next, I'm going to now, looking to divide these, I want to still simplify what's inside the parentheses, so I'm going to use the fourth law. X is going to stay up top, and when I subtract, I get a 5. Y is going to go in the bottom, and when I subtract, I get y cubed. Z is going to stay on the top, and once again, when I subtract, I get a power of 4. Once again, remember, why are we doing this? Because we have to subtract these exponents because the variables are being divided. So, the last thing I'm going to have to now do is I have to go and distribute the outer exponent of 3 on all the bases that are inside. So that would give me x to the 5th cubed, z to the fourth cubed, and of course y cubed cubed. And so now the last step that we would have to do is actually the second law, because we have a power to a power, and when we have a power to a power, we want to multiply those powers. So I would get x to the 15th, z to the 12th, divided by y to the 9th. And that would be your simplified expression. So we went from here, and we simplified it to here, okay, using the laws of exponents, okay? Like I said, I try to follow the order of operations in that I work inside my parentheses as much as I can. I want to clean it up, okay? I started by getting rid of all the negative exponents, because I know in the end I can't have any, all right? And that was a simple thing to do, just switch the position. Then I used some laws of exponents by subtracting the powers, and then I distributed the outer exponent, and then finally, power to a power, we multiply. All right? So that was section 6.1 and 6.2, the 7 laws of exponents. Okay? Like I said, each law by itself isn't so bad. It's basically performing 3 operations, adding, multiplication, and subtraction. But it's a matter of knowing when to add, when to subtract, when to multiply. What do you do with negative exponents? Okay? That's what makes it a little bit tricky. The more complicated the problem, the more steps, the more laws are going to be used. So take your time with it. Work through the homework problems that go along with these 2 sections, all right? And feel free to email me any questions or concerns that you may have. Until the next time, be well.